Hello students, let's talk about polyprotic acids. Thus far we have only talked about monoprotic acids, and monoprotic acids have only one ionizable hydrogen. For example, HF. It only has the capability to be able to release one hydrogen ion, or of course react with water to create H3O plus, and then we just have its conjugate base. Well, there are diprotic as well as triprotic acids. So this is an example, carbonic acid of diprotic. There are two ionizable hydrogens. Phosphoric is triprotic, three ionizable hydrogens. When these acids undergo ionization, they only release one hydrogen ion at a time. So for example, phosphoric, it will create one hydronium ion, still a 1-to-1 ratio, and then its conjugate base of H2PO4 minus. However, in the presence of these species, the H2PO4 minus itself will create an additional hydronium ion, releasing the second ionizable hydrogen. And then we get HPO4 minus 2. And then the HPO4 minus 2 can release the third ionizable hydrogen. Still a 1-to-1 mole ratio. All right, so the release of the first hydrogen, we would describe with Ka1. The release of the second would be Ka2. The release of the third would be Ka3. The conjugate base of the first acid releases the second hydrogen. Then this conjugate base releases the third. And then, of course, this, as phosphate, doesn't have the ability to release any more hydrogen ion. So the consecutive ionization stop. The release of the first hydrogen ion happens to the greatest extent. With polyprotic acids, the release of the first hydrogen ion is from the strongest acid. Ka values of consecutive acids decrease in strength. If we look at carbonic, we go from 10 to the negative 7th to 10 to the negative 11th. Your phosphoric, negative 3rd to negative 8 to negative 13. So usually the consecutive Ka values decrease in strength by at least 10 to the 3rd. So about 1,000 times weaker in its ability to ionize. Most acids that we'll deal with that are polyprotic only release or diprotic. So we'll just have two reactions, two ionizations that will be Ka1 and then Ka2. All right, so how do we deal with these kind of acids in problems? Well, what if we were tackling a question like is given to us on the first page of polyprotic acid calculations. So imagine that we have a 5 molar polyprotic, so it's H3PO4 solution. Now we know usually we're just asked for the pH of the solution, but here, just to go through this exercise, we're asked to express the concentration of all the successive acids and the final conjugate base. Here are Ka values that I copied from the page before. So we dig in first, starting with the 5 molar phosphoric. We know this being the strongest acid, it will happen to the greatest extent. So I did that work here, just a straightforward ice table using the first Ka. It does follow the 5% rule, even though that's a fairly high Ka value for a weak acid. Concentration of hydronium ion, and then my pH. Pretty low, huh? But again, that's a pretty high value for a weak acid. Now, just like we learned before, when you have a mixture of different acids, which is what we have here. So this is our quote-unquote first acid, the Ka1, our second acid, the Ka2, and our third acid. If we're asked for pH alone, remember we only have to deal with the strongest acid. Well, why is that? The release of hydrogen ion and creation of hydronium, this is present in the solution and will discourage the further ionization of the consecutively formed acids. Let's show that. So, if we were asked for pH, we would be done. But since we're asked for other things. Now, the stronger acid created these concentrations. So it is these that begin initially. That's the conjugate base of this, which is my second acid. But I'm also going to begin with 0.19 molar of this. So we know if we start with some of our product, it discourages ionization, common ion effect, 0. So minus x plus x plus x, 0.19 molar minus x, 0.19 molar plus x, and x. And then when I plug in, can we already see what's going to happen? So I need to check the 5%. And when I solve for my x here, it is 6.2 times 10 to the negative 8th. And that, of course, passes the 5%. And that will be the HPO4 minus 2. Now, if we see, per the number of sig figs, we would not need to add this to the hydronium ion that was created previously. So if I'm keeping track of my different concentrations, okay, the problem asked us to find the concentration of the phosphoric, the hydronium, get our pH, and then the consecutive ions formed. This, we would make 5 minus the 0.2, so this should be 4.8, huh? And then our hydronium ion, we found that this won't add any sig figs, or because of sig figs won't change the value. So the hydronium will be 0.19 molar. So we can continue to say the pH of our solution will be this. Okay, so if we take a look, this also will not change that value. So our H2PO4 would be 0.19 molar as well. So let's see if the creation of this allots very, very much to changing this to be our concentration of the HPO4 minus 2. So to continue to find then what this final concentration will be and this final concentration will be, if we do the ice table here. And so the creation of this would give us 6.2 times 10 to the minus 8th molar. However, this concentration continues to be what our original gave us, 0.19 molar. And then we haven't formed this yet. So minus x plus x plus x. 0.19 molar plus x. And then x. And then we insert 0.19 molar plus x times our x over 6.2 times 10 to the minus 8th minus x. This is plus. And we need to check our 5%. But when we do our math, our x value here is 1.6 times 10 to the negative 19th. Whew. So that definitely will not change this value. So our HPO4 minus 2 will simply be this concentration that we formed. This, of course, will not add anything to our concentration of hydronium, but this will be our concentration of our phosphate ion. So, going through this exercise shows again, if we're asked for the pH, if it is a polyprotic acid solution, even if our first acid is fairly strong, for the grand majority of polyprotic acids, we only have to consider the first ionization to get pH, and we'd stop. But this problem asks for consecutive values of concentrations, and we can see how this influences the further ice tables because of the common ion effect. There is only one exception to a problem like this. So usually we know we're only asked for pH. We only have to consider our first ionization. But sulfuric acid. Sulfuric acid is our only polyprotic strong acid. The Ka is ridiculously large, so we don't even give it as a value. And the Ka2, that's a pretty healthy, strong, weak acid. All right, what if we were asked to find the pH of a 1 molar sulfuric acid solution? We just have to know as AP students that sulfuric acid is the exception to what we just went through. All right, this is complete ionization. So we know that, and I'm not going to write water in these ionization reactions, that 1 molar will liberate 1 molar of hydrogen ion and 1 molar of the bisulfate. All right, so from here, hydrogen ion, 1 molar. However, okay, even if we have the presence of 1 molar from the complete ionization of that, and we start with 1 molar of this, we will get substantially enough per this Ka, 1.2 times 10 to the minus second. And we can see where we're going with this, but we'll go ahead and do the work. And the X here is 1.2 times 10 to the minus second, which does pass the 5% rule. Okay, so that will be the concentration of sulfate, but this is the additional hydrogen or hydronium ion concentration. And we can see that then that this adds 1/100th of molar. All right, so pH, negative log, and we'll do that of the 1.01 molar, and that will give us negative 0.004321. Now, the pH of just 1 molar would be 0. So we've added, a 100th of a mole per liter. That's significant as far as acids go. So for sulfuric acid, it is the only polyprotic acid where you have to consider the first and the second ionization reactions. Why? Because complete ionization, because it's a strong acid with the release of the first hydrogen. And then the second is a pretty big Ka value for being a weak acid. Okay, that's an introduction to polyprotic acids.